before these force fields, before these ML force fields really took off, the gold standard is first principles molecular dynamics. That is our microscope into computational microscope into how materials work. And so I highlighted just 3 areas where this kind of computational science has really made a difference and allowed people to either push the boundaries of where experiments can't go, or to connect experiment and interpretation. So one example is phase diagrams. So ask the most simple thing you can ask about materials is a certain temperature or pressure. What state are they in? Are they a liquid? Are they a solid? And solid, what kind of solid they are? So this is carbon phase diagram out to 10,000 degrees and the 2,000 gigapascals. That's 4 times higher than the pressure at the Earth's core. You can't do experiments under these conditions, and yet by executing quantum mechanics and executing molecular dynamics with the DFT models, we can actually discover the structure of matter in these conditions. Aqueous solutions of polyatomic ions, or complex ions, is another area where you have experiments, you can study these systems, but the experimental probes are not sensitive enough, not discriminatory enough to tell you about the atomic structure, the solvation structure, the reasons for a certain observed diffusivity and so on. And surface science is another area which is a huge part of experimental science. You can get nearly atomic resolution. These are molecules, individual organic molecules on a titanium surface, but you don't resolve the atoms, you don't resolve the bonds, you don't get to see what happens in its detail when bonds are formed and made. And the computational calculations, typically with DFT, allow you to do that and sort of connect these 2 worlds. There are many, many other properties from the thermal and dynamical stability, catalysis, drug properties have been mentioned in the question session, and of course semiconductor defects, and many of these, of course, underpin huge industries. And we can all, and first principles, DFT-based molecular dynamics is applicable and is very successful in all these fields. But there is, of course, a cost to this, right? So that's what machine learning really helps with. To give you a sense of how much DFT costs, a low-level DFT calculations, nowadays we usually think that I can do 100 atoms on one compute node and it will cost me 1 hour to get the energy of a single structure. And it scales cubically. So this is why it's hard, even as computers get faster and there's more cores on a chip, it actually is very slow going if you're going to count on that to allow you to do bigger systems and longer timescales. But those low-level DFTs, although they are very good for many things, they're not good for everything. And if you want to do a high-level DFT calculation, something like what OMO used, then that has a 20 times prefactor compared to the low-level one out of right away, and scales as n to the 4. And the gold standard, which is sort of a level of quantum chemistry that would say will get you most properties, actually scales as n to the 7. And doing these calculations typically at this level, so the low-level DFT level, is actually how most academic computers are used today. So this is a picture of a couple of years old, but the picture hasn't changed very much, of the percentage use of the UK's national high-performance computing facility. And 35% of all cycles is used by a single program called VASP, and it does molecular dynamics with DFT. And if you add up all the other smaller bars, altogether, these quantum simulations, so on this sort of accuracy versus timescale, is a hierarchy of modeling, and these are the quantum simulations, these are force field simulations. All of this takes up about 40% of the UK's academic computer time. So when we do MD, we take the positions, then when we do ab initio MD, so real quantum mechanics, then we compute the Schrödinger equation solutions, and that gives us forces on the atoms. And we iterate. And this is the expensive part, which is why 40% of the time on the supercomputer time is taken up with that. And that, all of that is thrown away at each loop. So everything you compute here, except the forces, all the wave functions, all the densities, enormous amounts of data that is generated and needed to calculate the forces, is not used as you go around that loop millions and millions of times. So we're trying, what ML force fields try to do is just not do that at all, but do it. Take the data that's calculated once, fit the model, and then just go around in this tight loop, predict the forces from the positions directly. It's a function fit. It's, as Brandon said, it's regression. We're trying to make a high-dimensional regression. So from sort of a 3n-dimensional space, n would be the number of atoms, to R, so a real number, the energy. And of course, this idea isn't new. Chemists have been doing this for a long time, but for very small things. So scaling is a popular word. So in a sense, we try to scale the idea from being able to do it for 3 atoms, 10 atoms, to 1 million atoms. And that was the real question 20 years ago, whether this is possible. Can you do this kind of scaling of fitting these functions for large materials, large molecules, molecular assemblies? And we want to do complicated things. So here's a very strange molecule, and I want to study its properties. Here's a little battery with cathode, anode, and electrolyte. And I want to study the processes, all the atomistic processes that go on. I mean, this is too small to have an SEI in it, but it's just an illustration of the kinds of things we want to do. Let me show you an illustration of how we did this before foundation models, so up to about 2 years ago. And yes, as I think Sam said, it is there and it's possible, but it was very, very painful. So this is kind of a flow diagram of how you study something. The example here is catalysis. Here's a surface, and we want to study this reaction. It's a hydrogenation of CO2. Take CO2, it binds to this surface, and you feed hydrogen in and make a more useful molecule that you can use as feedstock for chemical processes. And in order to make a model that can simulate this, we have to go through a lot of steps, active learning, basically, do molecular dynamics, generate individual data, structures, using an active learning loop, fit data until the model is sensible, and then when it becomes nonsense, then you fit more data. So, and then you keep doing that in this, over this long, long process. And when you achieve it, if you're then you can actually get the model to do the right thing. So here are the steps of all these of this reaction, and you see lines that are matching. One of them is the DFT line, and after 700 configurations are generated, we can reproduce that line. In fact, you see one of these barriers for one of these steps is different. That's where we use the fast model to try and find a new reaction pathway from here to here. This was previously the biggest barrier, so the rate limiting step for this process. And if you have a very fast model that's 10,000 times faster than DFT, then you can actually do searches and find a better pathway. And this purple one is actually 40% lower. And therefore, the prediction for the rate of this process changes dramatically. So I will not talk about the MP0 model, and Sam did that already. But just to say that 2 years ago, this has all changed, because we don't need to go through that active learning loop. Now we have these foundation models, and we still don't really understand how they work and why is it enough to train on very small crystal structures and get a model that can do all these things. That's active research. But that state of play from about 2 years ago is that we have force fields that cover the whole periodic table for materials. It can simulate thousands to millions of atoms. It's fast enough to run tens of nanoseconds, so that's 10 million steps per day. And it's accurate, especially when you fine-tune it. So if you fine-tune it with a tiny amount of new data, then it's good enough to do real science on it. The data set that achieves this is large, but it's diversity that really helps. So that's what we've learned over the last 2 years, is that in order to have this extrapolation capability, it's the data diversity that matters. You can get away, you don't need not even the 1.5 million material structures that was available at the time. You can run it just on 150,000 structures, as long as they're all different and cover the periodic table. You get the same quality in this model, that it can extrapolate and simulate anything that you like. And currently, in this space, people are engaged in this, exploring the Pareto front of accuracy and efficiency. Distillation was mentioned, and it's going to be a big part of it. All of these models are short range, so some sort of charge self-consistency, so electrostatic interactions, are important for some applications, not for others. And the biggest blocker for improving the material models is actually the DFT. So doing better job of quantum mechanics, doing a more so I would say DFT is definitely not dead. DFT is living its second life because now it's worth doing a really, really expensive and accurate DFT, which was perhaps not worth it before. Because if you had to do the MD with the DFT, then it has to be cheap. And now it's just an upfront investment. So actually, I think DFT research and electronic structure research is going to be reinvigorated by this, because now we are not forced to use it in a very inefficient way, but it's used in the best way possible by generating data for these surrogates. So let me give you an example of what is possible when you have these models. This sort of study would have taken a year or two before if we had to generate the data from scratch, but actually it took just a couple of weeks for a student who was proficient in using these models. So this is a study of this MOF structure. It's for CO2 capture. This is the structure of the system. And this is a combined experimental simulation study, which is actually sort of how these, it's material science at its best when you're not siloed away into the lab without atomic scale understanding or into the computational work office that you do in an office, and you have no contact with experiment, but the two the two groups work together, and that's what happened here. So this is the material, and there's a new technique, well, relatively new technique of oxygen NMR. So you're probing the local environment of the oxygen molecules, trying to understand how CO2 gets absorbed. And this is the signal that you get. And when you try to interpret it, it turns out that that's very hard. These peaks are not in the right place compared to standard tables of what you should get when you see the various oxygens in this system. So this is what we're trying to study here. There's this zinc atom, there's an OH group, and the CO2 comes in and reacts with the OH group and has various ways of dancing around this reaction site. And that motion of the dance of that little CO2 molecule is what's sort of messing up the signal. And there are different timescales involved. So on this series of plots, I always have the experimental plot in black, and under certain assumptions, the colored plots are the identified signals for belonging to certain groups, certain local environments of oxygen. So if you just do DFT and you geometry optimize these structures and predict what the signal should be, you get these colored lines. It doesn't match. Then you say, okay, I've understood that there are multiple states here, and the system can go in between them at a certain rate that you can try and compute from DFT. Then you get a different set of lines. Still doesn't match. What really happens is that the landscape of the molecule is very complicated, and you need to run MD. But DFT is too expensive. So now you turn on the ML model that is actually a fine-tuned version of the big foundation model. And now you can study how, if this is the potential energy landscape, how the system moves around and explores many, many different conformations. And you see, again, a change in the line shapes, and now you start to see some matches, but there's still some peaks that are shifted. And then finally you combine all of these ideas, so you have some molecular dynamics in a certain local configuration, and then you take into account jumps between different kinds of states, and that now gives rise to the prediction that matches the experiment. And you can, of course, go back and ask what are the timescales of all these different motions, and you can assign each individual peak. When you then change your structure, now you understand the spectrum, you understand where each component comes from, and you can interpret your experiments. Let me show you three drug discovery examples, because we haven't really talked about the other that came up in the questions. So this is in the work that I'm presenting here was done by Angstrom AI, which is a startup here in San Francisco. Oh. And there are 3 hard tasks in drug discovery that can be solved by computation. One of them is solvation-free energy, solubility. You imagine that you're going to make a drug. Here's a proposal for a compound. How soluble is it in water and in fat? And the solubility in water is going to basically determine the basic rate of metabolism, so how quickly are you going to excrete it? And the difference between solubility in water and solubility in fat is a proxy for how quickly it's going to enter into your cells. And that's called log P or log D when you take the pH into account. And you can do that experimentally, but it's expensive and you have to make the molecule first. Let's try and do that computationally. The second task is organic crystal structure prediction. So that's when if you manufacture a small molecule drug and you take it as a tablet, actually that tablet is a compressed powder, and that the powder is composed of crystals. And when drug companies get a license for a drug, before they get a license, they need to demonstrate that they know what is the arrangement of the drug molecule in those crystals. If you don't know, then you can't manufacture it reliably. It turns out that most organic compounds can crystallize in multiple crystal structures, and those have different solubilities and different physical chemical properties, and you need to know in order to be able to predict the effects of the drug. And the last one, the sort of holy grail, which is the hardest, is ligand protein binding free energy calculations. Is this drug actually going to bind to the protein that it was designed to target, and how strongly? And that is very, very difficult to do. I'm going to talk about the first 2. So let me skip some of the equations. Basically, we need to modify the models to allow, instead of the real physical repulsion between atoms, we actually need to allow atoms to kind of overlap, because that's the technique that is being used for solubility. But just ignore all this, focus on the results here, that these are very small molecules, and we go up to ibuprofen and caffeine, and the blue bars are experimental hydration-free energy. So taking how happy is the molecule being in water. And these orange and red curves are existing empirical force fields. Super fast, super well established, and not very accurate. It's okay for very small things like ethane and methane, but not for larger things that are actually drugs. And the ML model, in this case, the model built in my lab, the MACE model, actually gets these within experimental accuracy. So you don't actually have to do the experiment. You don't even have to make the drug. We can do it. We can do more compounds. So there's a database called FreeSolve, where about 700 compounds which have experimentally verified solubilities, and we computed a lot of them, and this is the prediction. Again, the established classical force field is the green, and it's just really not accurate enough. Log P is something similar, but instead of the solubility in water, is the difference between solubility in water and fat. The fat here is the fatty substance here is octanol, and it's kind of a proxy for your cell walls. And again, the gray here is the empirical force field, what's currently being used by drug companies, and the blue is the experiment, green is the model. So we have experimentally accurate computation. We bring this task from the lab over into the computer. Drives down the cost. The second task is crystal structure prediction. So we just started working on that recently, and there DFT is king. So you do a lot of search of what the organic molecule, how it could crystallize, and then you rank it with DFT. And there are DFTs, versions of DFT, that are sort of established as good enough to do that. So the name of that is here, B86BPBE plus XDM is a version of DFT that has been verified. And the compounds here are from the blind test competition. So that's a competition run every 2 years, where people create a set of new crystal structures, but they don't release the structure. And they wait, they give the compounds, the molecules, identities to computational researchers who then try to predict the crystal structure, and there's a paper written about the results every 2 years. So this is an aggregate of the last 7 compounds, many of the compounds in the last 7 blind tests. And so the target here, this is the ranking with respect to experiment, and you see DFT is quite good. It gets you rank 1. It has some blind spots, so this particular version of DFT is not always good, but that's where it's not, it's sort of understood. When you make a surrogate for DFT, the target is, it would be nice if we could get everything rank 1, but at least let's try to get as good as the DFT, because that's when the ML surrogate is successful. The Masoff model is the organic model that is very good for solubility. It's not quite good enough for crystal structure prediction. Often it's fine, but there are big outliers. So we make a crystal structure and prediction version of the MACE surrogate. It pays special attention to both the intramolecular energy, the conformational energy of the molecule, and the intermolecular energy, the interaction between the molecules. And that gets you much, much, much closer to being a replacement for DFT, which is the dominant cost here. So we're also extremely enthusiastic users of OML and are making new models. So here's a recently introduced GMTKN benchmark is how accurately do you get the energy of small molecules. And we have 2 models here. The red one is without electrostatics. The turquoise one is with explicit electrostatics. And you see that, and the gray ones are the UMA models from Meta. And what you see is that we can get models that are, these MACE models are as good or better than the Meta models, and we are getting close to, but not quite yet reaching, this blue line, which is the DFT that OML is based on. So this is one point I disagree with Sam, is that OML is not the final data set. We need higher levels of theory to fine-tune and do even better. This is, for example, in this overall benchmark. But there are other benchmarks in which there is room to improve. But no question that OML is a different world after OML. There's nothing like it before. This is for single molecules. The non-covalent interactions, so molecule interactions, actually shows an even starker contrast. So here, if you don't include electrostatic interactions, you still get these very big errors, but the turquoise bar is just very, very, very small. The errors here are really approaching that of the DFT in most cases. So we are also huge fans of the multi-head learning, combining materials and molecules. I think we are, as a community, are just at the very, very beginning of that. It's a very hard thing to do. But there are very, very encouraging results. So when we combine all of the different training sets, and in this case, we don't pick a different task. We don't pick a different version of the model for each task. We actually demand that we get a universal approximation of quantum mechanics across all these systems. We can make a model called MACE multi-head OMAT. It's the OMAT head. And you actually get a significant improvement over anything else that's on the market. So that includes ORB, that includes Mattersim from Microsoft, it includes the UMA models. So we get sort of rank 1 accuracy, except in one area where it's rank 2 across the board, and without telling the model what task you want, it's the same model. So you can actually take molecules and combine them with materials, which is what a lot of people want to do. So take molecules, put them on surfaces, and so on. Exciting times is all I can say. I agree. Thank you.